Okay, now let's move on to see another question. Now this question, what's the difference between this one and the previous one? So for this question, now the boundary with the surface charge density. So the previous case, charge free, not free of charge. Okay. Right. Now on the surface has some charge, right? Has some charge. So the corresponding part here. Again, for the tangential direction, the same, right? It will be the same. The electric field, right? Now the only difference for this, the normal direction, perpendicular to the boundary direction, right? Perpendicular to the boundary direction. Okay. So then let's look at this. Now, again, so for the E1x is equal to E2x, right? E1y is equal to E2y, right? E2y. So now the difference is here. So we need to apply this equation, right? E1, this E1n, E1z minus E2z equal to rho s, right? Then set those values into this equation, you can obtain E1z. So then combine the E1, E2, E1x, E2x, and E2z, E1z, right? You can obtain this electric field. It's actually quite straightforward. Right? Okay. Then this one, 6. Six equal charge. We have 6 equal charge. Actually, this is for this one, Coulomb's law should be applied. 6 charge, this charge, this charge, this charge, this charge, this charge, this charge, and this charge, right? And this charge. So means at the vertex of the regular hexagon, a small charge placed at the center, right? What is the force on this charge? Okay, if we have 6 charge, what is the total force? If we have this six charge, what is the total charge? Our total force.
We have 6 forces. 6 forces acting on the center.
Yes. Now what is the total force?
0. Assuming the 6 charge is equal.
Right. Now 6 charge are equal positive Q. So then, for instance, the top and the bottom will be cancelled, right? This also will be cancelled. This also will be cancelled, right? Okay? Right. Then for that case, the total force will be equal to 0. Now, for instance, this charge is removed. Okay? What is the force? Total force without this one. Now without this one. Actually, this will be cancelled, right? This will be cancelled. Only this charge will have the net force. Right? What is the net force? attract, right? So it's utmost direction, right? Okay. This is actually quite straightforward. I will not go to the detail. Then let's look at this question. This is Gauss law for spheric coordinate. A sphere, and a radius A has volume charge. Now notice this volume charge is not uniform, right? Not uniform. Not uniform. Okay. Then you have to use the integration. Okay. To calculate the total charge enclosed by the Gaussian surface, right? Okay. At the right hand side, when we apply the Gauss law, right? Okay. I, the distance from center of the sphere. Derive the expression for electric field inside the sphere. When there are two radius. One is inside the sphere, then outside sphere, right? Okay, we have this sphere, then charge, now charge, volume charge, not uniform. You have to do the integration. Okay, we have this charge. First is draw the Gaussian surface. This is region 1, right? Therefore, region 2, you have region 2, right? Region 2, okay? This for this for R greater than A, okay? Now, for this one, as mentioned, left-hand side in spheric system, left-hand side. So by using the Gauss law, right? Left-hand side, okay, for this one, for region 1, right? This region 1. Okay, left-hand side, no matter for region 1 or region 2, left-hand side always the same, right? Okay. Left-hand side always the same. Right? So then how was the right-hand side? Right-hand side, for instance, for this region, right? The right-hand side, then is this charge density, right? Then do the integration, in the volume integration, right? Okay, turns out, we can recruit to, so some students don't have time, to this too. I cannot help, right? That I cannot help. If you don't have the time, how can I help you? I cannot loan my time to you, right? Okay, so basically, to calculate the charge, total charge enclosed, for instance, similar to this case. Actually, I have already explained here on that note. Similar to this. This is the volume integration. Now this is the charge, volume charge, right? Cell into this. So now it's only the integration limit are different. Theta is from 0 to pi, phi is from 0 to 2 pi. Then for this one is from 0 to 8, right? For region 1 is 0 to A. For region 2, then maximum is up to here, right? Maximum is to here. For this is also the region R. Therefore, for region 2, the maximum is the radius is A, right? Okay. So therefore, this is A. For this case is R, right? The right hand side, total charge. This total charge, right? Then for this case, this total charge. So then you can calculate the relationship. Okay? It's actually quite straightforward. The left hand side and the right hand side. For right hand side, if the charge density is uniform, you can use the volume of the sphere times the charge density directly. Right? If the charge density, so actually this is a common mistake. Common mistake. Almost half the students will make the mistake. Right? Although we highlight many times in the past. Right? So some students still use, for instance, if the given charge density is not uniform, right? Not uniform. Some students still use the uniform. Means just multiply the volume and the charge density. Definitely not correct, right? Okay, not correct. You need to use this integration to obtain the charge density, the total charge. Okay, right? The total charge. Now move on to the second picture. The charged sphere is subsequently placed concentrically inside a metallic spheric shell. Inner radius B, out radius C. Derive the expression for the electric field in the exterior region for the following cases. Where spheric shell is left on Earth. Another is after the spheric shell has been Earth. Means connected to the ground plane, right? Okay, means one case is this not is connected to the ground plane, right? If this is connected to the ground plane, then yes, enclosed, no charge, right? Means then outside electric field will be equal to 0. Okay? If ungrounded, then need to look at the total charge enclosed, right? What is the total charge? Actually, should be the same as before. Should be the same as before, right? Okay, should be the same as this. Okay, right? Without oscillatory, right? So outside should be, you see the total charge, right? Inside this. Okay. So very important is key point. The key point for us to apply the Gauss law is to understand the total charge enclosed, right? The left hand side should be, for instance, should be the same. For cylindric case, should be the same, right? For spheric also should be the same, right? Okay. Actually, once you can write the left hand side, also we can avoid some marks. So those, right? You should recognize the question is in the spheric system or in cylindric system, right? Okay? Quite a few marks. could be given. Right? 25 marks, for instance, the big question could be 4 or 5 marks if you can write the left-hand side of the possible. Right? Okay? Right. So what you can apply is you need to recognize, right? Definitely the question is the linear system or the square system or rectangular coordinate. Right? Okay? Then the left two questions is small question. This is small one. One is the current flowing through 100-meter long conducting wire of uniform cross section and the density, this current flow, for instance, a wire and the current density, find the voltage drop across this wire with the wire material and the conductivity. Right. Okay, so Ohm's law, those law will be applied. Okay, now let's go through this one. Right. So what this relationship, right? The current density and electric field linked by the conductivity, right? Okay, in the meantime, so then from here, you can obtain the electric field and current density. In the meantime, the voltage is equal to this. Okay, just now, some students asked me the relationship. What is E, what is D, what is H, what is B, right? Okay? What is the electric field? What is the electric flux? What is magnetic field? What is magnetic flux? Okay? What's the difference of the electric field and the magnetic field? What's the difference? The difference, they come from different sources, right? Okay? From different sources. So charge will produce the electric field, static charge, right? Okay? Then moving charge actually will form the current. Okay? Moving charge. Then current will produce the magnetic field. Right? On the other hand, magnet also will produce magnetic field. Okay? Right? So then also students ask me what is the voltage, right? Okay? Here the voltage for the simple case, the voltage, right? Actually, previously also we learned this, right? This is a set of tools to calculate the electric field. Well, sometimes it's easier to calculate the voltage, right? So then from the voltage you can obtain the electric field. Previously we have actually the relationship is given here. The voltage and the electric field, right? The voltage and the electric field. Okay? So this is so-called electric field times the distance. So here, for this, and then from there, the relationship. This is a gradient of the voltage. Okay, will give us the electric field. So also we mentioned sometimes easier to obtain the voltage. Right? For instance, for this case, case, for this is also very classical case. So for this case, easier to obtain. This is parallel plate. Also just now, once you are the parallel plate. Okay, the so-called Poisson equation can be applied. Then from applying the boundary condition at this electrode, the voltage can be obtained. But then from there, you can obtain the